Okay, now we're going to look and see how dominance reasoning would play into the decisions of row and column here. Notice that for row, R1 and R2 stand in no relation of dominance. R1 has a better outcome for row in C1, 10 as opposed to 4, but R2 has a better outcome in C2 than does R1, 2 plus 2 as opposed to plus 1. So neither of these rows dominate each other for row. Neither R1 nor R2 dominates the other for row. But look for column. Notice that C2 strictly dominates C1 for column. If row plays R1, column does better playing C2, -1 as opposed to -10. If row plays R2, column does better playing C2 than C1, -2 as opposed to -4. So we know, since column is a perfectly rational agent, column will never play C1, and row, who knows the total outcome of the table and who knows that column is a perfectly rational agent, knows that column will never play C1. Look also at C2 and C3. Column does better playing C2 than C3, -1 as opposed to -3 if column plays R1, and column does strictly better playing C2 rather than C3 if row plays R2. So column also will never play C3 because it's strictly dominated by C2. So column will play C2 as a perfectly rational agent. Column will play C2. Row, as a perfectly rational agent, who knows that column is a perfectly rational agent, knows that column is going to play C2. So row, therefore, will play R2 in order to maximize row's payoff, knowing that column's going to play C2. Column knows that this is what rows is going to play because that's the obvious solution for a rational agent, knowing that column's going to play C2. And so this game, using dominance reasoning, has a solution. Its solution is the pair R2, C2, and its value equals +4 for row and -4 for column. And the game has been solved. We know exactly what perfectly rational agents will do, and we know exactly where they will end up via dominance reasoning.